Today at Training School for Children, we're going to be talking about the basics of geometry. And what we need to do first is get some vocabulary so we can understand what we're talking about as we go throughout this lesson. So the first thing we're going to talk about are points. These are the simplest figures in geometry. Although a point doesn't have any size, it's often represented by a dot, which does have some size, obviously, but keep in mind, the actual point does not have size. So we use a dot to visually represent it, a figure that doesn't have size, and we name them with capital letters. So here are some examples of points. We have point A, B, C, D, and E. And as you can see, there are dots there. And even though this does have some size, point A has no size. And all geometric figures are going to be made up of our points. So another familiar geometric shape is a line. And lines are made up of points, and they're straight. The arrows on the ends of the figure show that they are extending forever and ever. Although the picture of the line that we have here, both of these, do have some actual thickness on our screen, lines themselves do not have any measurable thickness, unless it is explicitly stated that it has some type of thickness, okay? So the following are examples of lines. There are two ways we can name these. The first way is by using a single lowercase letter, such as W here. The other way is by naming the points on the line. So if we had 2 points on this line, so if we had a point A here and a point B here, we could name this as line AB or line BA. And notice the representation of this has a line, kind of a picture of a line on top of it, denoting that it goes on forever in both directions. And normally you would list these in alphabetical order. So AB, line AB here, would be the typical representation of this. But the other way is also correct, BA. Again, this is just more typical. We're going to talk about number lines just for a second so we can understand the next concept, the next definition. So number lines formed when we assign numerical values to the points on the number line. So on this number line, we have point A at -2 and point B at 3.5 or 3.5. And you can tell that if we wanted to connect these, we would have a beginning here and an end here. Or if you were thinking about the other way, this would be an end here and this would be a beginning, whichever way you want to go with this, right? These are endpoints. A and B would be endpoints, and we would have a measurable distance in between those two things. Okay, so that's going to help us understand line segments. Okay, segments are made up of points and they're straight. And what distinguishes them from a line is the fact that they have a definite beginning and an end. Okay, so if we look at the line segment on the right, line AB, we have 2 endpoints, one at A and one at B, and they're connected in between. And it does not extend past those endpoints. They stop it from continuing. And we have a definite distance here. And when you write these out, you write it as AB, the line segment drawn on top of it. Notice there's no arrows extending it out. Or BA, and again, normally you write these alphabetically, so this would be the more typical way of writing it. But again, both are correct. And if you look at this, we have 2 line segments here. So we have a vertical line segment here with QR or RQ, and we have a horizontal line segment with RS or SR. And again, remember, alphabetically is typically the way you go in math. So line segments, what's different from these segments from lines? They have a definite stop and start called endpoints, and you can measure that distance. Okay, so if you look at this, we have a segment that we can make here between point B and point C, and we would call this line segment BC or CB, and you could actually measure this. B would be an endpoint, and C would be an endpoint.
These hybrids are called rays. Rays, like lines and segments, are made up of points and are straight. A ray is different from a line or a segment in that it begins at an endpoint and continues forever in one direction. The following are examples of rays. Notice the ray on the left starts at the endpoint A and continues in the direction of B, infinitely far. So this arrow lets you know this keeps on going. When we denote it, we write down the letters for the points, A, B, and we draw an arrow above it, and the arrow goes in the direction of B, where it continues forever. Notice the endpoint's A, so our endpoint of the arrow above this, of the ray above this is above A, endpoint. No arrowhead on this, above A. The one on the right here has 3 points, we have the endpoint C, and then two other points labeled on this. Remember, just like a line, we have an infinite number of points on this thing. So here we have one name for this. We start at the endpoint, C, and we could say we're headed in the direction of D. So this would be ray CD. We could have also said we started at C and headed in the direction of E. So our endpoint C, and we head in the direction of E. The endpoint always has to be the first letter there, and you draw the arrow above, the ray above it, and the direction it's headed. Now that we've talked about points, lines, line segments, rays, we can talk about angles. And in essence, angles are made up of two rays with a common endpoint. The point where they connect is called the vertex. The rays of the angle are called the sides of the angle. And there are various ways you can name an angle. For example, if we place a 1 in here, you could call this angle 1. And the way you do these, you use this symbol. It looks just like a little angle there. So you denote it with a little angle and then the name for it. So angle 1, we can name it by the vertex alone. So the vertex here is at B, point B. So this is angle B. Or you can name it with the 3 points. So angle ABC, or go the other direction, angle CBA. Notice the vertex is always in the middle when we're naming our angles, right? If we use 3 points. A plane is a flat two-dimensional surface that extends infinitely far. What that means is this goes on forever in the direction of side AB, extends forever in the direction of side AD, forever in the direction of side CD, and forever in the direction of side BC. Just like a point has no thickness, it's two-dimensional. It's hard to give a real-world example of this. If you want to think about it like drawing on a flat piece of paper, it's kind of like a plane, except that the plane itself doesn't have any thickness. Right? If you were to think about the edges of the paper going on forever, that would be more or less a plane, right? Because it has to extend forever too. Okay, let's practice drawing, denoting, and naming figures. So take a moment and see if you can draw each one of the figures that are denoted here. So go ahead and pause that video and see if you can do that. All right, so the first thing we have is line segment PQ. We can tell it's a line segment because there are no arrowheads above here. So you should have 2 points and a line segment connecting those, and then P and Q above those being the labels for each point. Next up, we have a line PQ. You can tell it's a line because it has the arrows on each end of it. So we should have our 2 points, P and Q, and then an arrow extending out from each one of those points. We have a ray next, and a ray has an endpoint, and our endpoint is at P. You can tell that because there's no arrowhead above P, and it extends through Q forever and ever. We have an angle, and it's angle PQR, so Q needs to be in the middle there, and then having a ray extending from that through point P, and also another ray extending through point R. And lastly, we'll need 3 points to make our triangle. Point P, Q, and R, and then we'll need to connect each one of those with a line segment to make our triangle. What are the names for this line? See if you can come up with the names for it. Go ahead and pause the video for a second. Okay, we can name this line with the point. We can name it line AB, or we can go reverse, BA. Normally alphabetically is the preferred, so AB would be the most common, or you could just name it with its lowercase letter here, line M. What are the possible names for this angle? Pause the video, see if you can come up with all of them. Okay, we could name it with the point at the vertex. We could name this angle R, or we could name it with the number inside of the angle, name angle 5. We could use all 3 points, Q, R, and S. Remember, R is the vertex, so that needs to be in the middle, so it would be angle QRS. We could go the other direction with this and say it's SRQ. Okay, see if you can name the sides of this triangle. Take a second to do that. All right, let's go ahead and do it. So we have line segment AB, so from point A to point B. And you could also call that line segment BA. It doesn't matter which way you go. Again, the preferred is alphabetically, but it's okay if you say BA. We have line segment AC or CA. And lastly, line segment BC or CB. All right, we're going to talk about polygons now. And a polygon is just a closed figure on a plane with at least 3 sides. And the sides don't overlap when we talk about polygons for the most part. If you do get a little further in math, you'll see that there are cases when we talk about this a little bit, but when we talk about polygons in general, the sides meet at their endpoints. And they're named by the number of sides they have. Okay. Triangles, quadrilaterals, pentagons, hexagons, heptagons, octagons, and so on. And if you look at the prefix on these, like the tri, 3 sides, quad, like your 4-wheelers have 4 sides, penta, like the Pentagon building has 5 sides, hexagon, like a hex bolt has 6 sides on it, and so on. Polygons whose sides and angles are all congruent, or they're all the same, are called regular polygons, and those are the ones that you're used to seeing, like your stop sign shapes, your yield signs, or anything that's going to be all the same sides, all same angle, are called regular polygons. And if they're not that, then we do have some other ways of classifying these. So let's start out by talking about triangles. In our polygons, triangles can be classified by either their angle measurements or they can be classified by their side lengths. So with the angles, if they have all the angles under 90 degrees, those are called acute triangles. If they have a 90-degree angle, then they're called a right triangle. And if they have an angle larger than 90 degrees or greater than 90 degrees, it's an obtuse triangle. And if you want to talk about them based on their side length, you have a couple of options. You've got the equilateral triangle. All sides are the same length. Isosceles, they have 2 sides are the same length. And then scalene have no sides that are the same length. And here are some pictures of those. You've got an equilateral triangle. Notice all 3 sides are the same. These little tick marks on here let you know if they have the same number of tick marks on them, they have the same length, okay? So all 3 of these are the same. Isosceles, these 2 sides are the same. And the scalene, they have none of these in common. Acute, if we're talking about angles, acute, all of these are smaller than 90 degrees for the angles. Here we have a right triangle on here. Here's a right angle there. And obtuse, this is your obtuse angle. It's greater than 90 degrees. Now let's go ahead and look at a couple and see if you guys can name them. Here's a triangle. Go ahead and pause the video, think about it, and see if you can name it. And it is an obtuse scalene triangle. So you could either call it an obtuse triangle, you call it a scalene triangle, or you could call it both obtuse and scalene. Notice it's got 3 sides that are different. So 1 tick mark, 2 tick marks, 3 tick marks. None of these are the same. And you have 1 angle that's bigger than 90 degrees there. Okay, here's another one. Pause the video, see if you can get this one's name. All right, this is an equilateral triangle. It's also an acute triangle. Together, it would be an acute equilateral triangle. What about this guy? You got it. It's an acute isosceles triangle. All these angles are smaller than 90 degrees, and you have 2 sides that are the same. Think about this one. Pay attention to the numbers that are on it and see if you can name this triangle. Go ahead and pause the video. That's right. It's an obtuse triangle because you have an angle here greater than 90. It's an isosceles triangle because these 2 sides have the same length of 4. And if you want to name it together, you would say the obtuse isosceles triangle is what it is. And lastly, let's try this one. Go ahead and pause that video. This would be a right scalene triangle. You have your right angle there, and then all of these sides are different lengths. Let's talk about quadrilaterals for a little bit. So here's some types. We have a trapezoid that has exactly 1 pair of parallel lines. You have a kite, and that has 2 pairs of equal sides, and that means same length. And those sides have to be adjacent to each other. It means they're touching, they share a common vertex, and each pair of those has to be distinct, okay? So parallelograms is another type of those, and we have opposite sides are going to be parallel to each other. That's where the name comes from. Both pairs of sides are going to, both opposite sides are parallel. And then subcategories of those, you'd have a rhombus. So you're going to have opposite sides parallel, and they're all four going to be the same length. A rectangle is going to be opposite sides are parallel, and you're going to have 90-degree angles in there. And then a square would be both sets of opposite sides are parallel, all the sides are the same length, and all the angles are 90-degree angles. So here's kind of the breakdown of that. You've got quadrilaterals, all of these fall into that category. And then it breaks down to kites. Notice that these adjacent sides are the same length. These adjacent sides are the same length. Parallelograms, the opposite sides, these two sides right here are parallel, and these two opposite sides are parallel. And then the trapezoid only has one pair of parallel sides there. These opposites are parallel. And then you can break down from there. So we go parallelogram down. So rectangles have opposite sides are parallel. And then the extra feature is they have a 90-degree angle for all of those. And then parallelogram going this way, rhombus, opposite sides are parallel. And then the extra feature here is they're all the same length. That's indicated by these little ticks on here. And if you go even further down, you have in the parallelogram family, you have a square, which opposite sides are parallel, all four sides are congruent, and all the angles are 90 degrees. Now, if we look at the trapezoid, you could have an isosceles trapezoid where you would have two of the sides being the same over there. Let's name some of these. So I'm just going to put the features up there, and you tell me what named it would be. Pause the video and come up with this. It could be more than one name, so don't think it's just one of these automatically. Four congruent sides, square or rhombus. Okay, here's another one. Two pairs of parallel sides. Again, pause the video. It could be more than one. So you have a parallelogram, a rectangle, square, or rhombus. Okay, what about exactly one pair of parallel sides? Go ahead and pause it. Trapezoid, you got it. Four congruent angles. Pause that video. I hope you got rectangle and square. What about opposite angles are congruent? You have to think about that one. Maybe go back and look at the flow chart. Okay, pause and come up with your answer. Rectangle, parallelogram, square, rhombus. All right, let's switch gears, talk about perimeter. So perimeter is the distance around a two-dimensional shape. Here we have a two-dimensional shape, a rectangle. You see our little figure running around the outside of that guy. Notice it's not zigzagging through the middle of it. Right, that would be area if we were talking about space in here. We're talking about the distance around the outside of that. And you can find that just by adding up all the lengths of those sides. And your units for this will be linear, which means feet, meters, inches, anything that you would measure a distance with, okay? Straight distance. Let's find the perimeter of these shapes. Here's a interesting one for you there. Go ahead, pause the video and add those up. Okay, hopefully you came up with 24 centimeters. Here's a little square for you. Find the perimeter of that, please. Okay, 28 centimeters. And lastly, here's a little rectangle. Find the perimeter of that rectangle, please. 20 units. Now notice on the last one, we wrote units. On the shape, it did not indicate what the units were. So when you write your answer down, you can just put 20 units. Area is the space inside of the two-dimensional figure. So not the distance around. It's going to be all the stuff inside of here, okay? The units are going to be in square units for area. So instead of seeing centimeters, you'll see centimeters squared, inches squared, meters squared, etc. You can think of this also as area as the amount of squares that have a 1-by-1 unit of whatever unit you're talking about that fit inside of that shape. So let's look at a shape over here. Here we have a big old square, and the units we're going with are centimeters on this. So the number of 1 centimeter by 1 centimeter squares that fits inside of this square would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 square centimeters fit inside of this shape. Right? It has a side length of 3 centimeters and 3 centimeters, which if you keep that in the back of your head, we're going to be talking about how to find these with a little math here. Look at this square. We can fit 1, 2, 3, 4 squares in this. If you look at this as 1 centimeter, 2 centimeters on this side, 2 centimeters on this side, and it has an area of 4 centimeters. So 2 by 2, answer is 4 centimeters squared. This was 3 by 3, answer of 9 centimeters squared. This is 4 by 4, and it says 16. Do you guys see the pattern happening there? It's the side, this side times the other side, right? So we have a side times a side. Well, that's going to be the formula for the area of a square. It's going to be side squared. So here's a lot of common formulas that you're going to see for some shapes that are pretty popular in your math classes and in your problems. They're very common. So we have circles. It's going to be pi times the square of the radius. So at the very end, you see the formula here. The capital A is used to denote the area. So capital A, area. This is your symbol for pi. And here's R for radius. So area for a circle is equal to pi times the radius squared. For a rectangle, the area is equal to base times height. You might see that as length times width. I like to say base times height just because it keeps in mind that the base and the height are always perpendicular to each other, and that's how you're going to be able to identify those. And that works for all of them. So your triangle, the area is equal to 1/2 base times height. The base and the height have to make a 90-degree angle when they touch each other, right? They're perpendicular. For a square, it could be base times height, right? Length times width. But because the sides are all the same, it's just side times side or side squared. For a trapezoid, this is probably the most unique one. We have the area is equal to half of the sum of the bases. So base 1 plus base 2, right? Divide that by 2 and then multiply it by the height. So in our formula here, 1/2 times the quantity A plus B, where A is base 1 and B is base 2, and then multiply that by the height of it. So let's practice finding some of these areas. So here is a figure you should recognize by now. This is a trapezoid. Your bases are parallel to each other. So here's base 1 and base 2. So we have 2 and 3. Your height is perpendicular, so it should come straight up to the base here and make a 90-degree angle. That's why we don't use the distance on these lines here, on these sides, because they're tilted and they don't make an angle here that's 90 degrees. So we need to have one right there showing that. So there's the formula filled in. We put all the pieces in there. And you can see 2 plus 3 is 5. Half of 5 is 2.5. 2.5 times 2 is 5. And the units, again, are squared on these. Here's another little figure for you. This is a little circle with a radius of 7 inches. So because we're talking about inches, we know our units on our area are going to be inches squared. We're always going to square those. So here's your formula with the radius filled in. I didn't put pi in there. In 6th and 7th grade, you're going to be using 3.14 or 22/7 to estimate pi. But in 8th grade, you're just going to hit that pi button on your calculator and use that irrational number. The symbol here that looks like a little squiggly equal sign, this is telling you it's approximately. So this is approximately 153 9/10 inches squared. And our last figure, this is a little rectangle, and we have 4 centimeters times 9 centimeters happening here in our formula, and that gives you 36 centimeters squared. So one of the things you can also do is you can solve these equations for a variable. So if you have a missing side and you know the area, you can work backwards to find the side length that you're missing, right? Whatever dimension you're looking for. So the way you do this is you simplify the side as far as you can. You're going to work backwards to isolate the variable that you're looking for using your properties of equality, like division property of equality, multiplication property of equality, and so on. And you can do that with the original equation if you know which one you're solving for. So if you have your formula for, let's say, a triangle, and you want to solve for the height, you can go ahead and just use the letters there, the variables, not putting any of the values you know, and work backwards to solve for that letter. Or you can put the numbers in and then work backwards to solve it. So here we have an easy one. This is the area of a rectangle or parallelogram in general. So area equals base times height. And let's solve this guy for h. So the first thing you're going to do is write down the original formula. This one we are solving for h. So we look at h and decide what operations are happening there with h. We have multiplication with the b. So we do the inverse of that. We're going to divide by b. And we'll use the division property of equality to do that. And then we're going to simplify. So b divided by b is 1, so we have 1h, or just h. And on the other side, we can't simplify that, a divided by b, and so we're done there. That would be solve for h. Here we have the formula for the area of a triangle. Again, we're going to solve for b here, so let's go ahead and copy down the original. And we've got a little multiplication happening and a little multiplication over here. So we're multiplying by 1/2 and multiplying by h. So we're going to go ahead and get rid of our fraction. If you see a fraction here and you're doing multiplication, you can just multiply by the reciprocal of that fraction, which just means you flip it over. So instead of 1/2, if you flip that, it'd be 2/1, or just 2. So you can multiply both sides by 2 using the multiplication property of equality, and then simplify to get rid of that fraction there. So 2 divided by 2 is 1. So you have effectively eliminated that fraction there. It's just 1 times b times h. So you have 2a equals b times h. Now we got to worry about the h over here, and that's multiplication happening. So we do the inverse, which would be divisions. We're going to divide both sides by h. And when you simplify that, you end up with 2a divided by h equals b. Here's a little bit more complicated problem. We're going to solve the formula for the area of a trapezoid for a. Okay, so copy down the original formula, multiply both sides by 2 to get rid of the 1/2 using the multiplication property of equality. We're going to simplify that. 2 divided by 2 is 1. And now we're going to get rid of the h. So we've got multiplication happening in between h and the quantity a plus b. So we divide both sides by h, use the division property of equality. We'll simplify that. We're just left with ab on the right-hand side and 2a divided by h on the left-hand side. We want to solve it for a. We still have a plus b, so now we'll subtract b to make that 0. We're going to use the inverse operation there. So subtract b from both sides. And when you simplify, you'll get 2a divided by h minus b equals a. So I'm going to turn you loose on some practice sheets. If you look at the links below, you've got all kinds of interactive websites you can go to practice this stuff. And good luck.
We are the Perfect Squares signing off. See you next week. Bye.